Hello, I'm Dr. Ian McCullough of Johns Hopkins University. This is a short lecture on neural anatomy. Our objectives today are to describe key brain regions and their cognitive functions, describe neural mechanisms associated with influence and persuasion. Now, neural anatomy is particularly challenging. There is a lot of research that's been done, and it's often like trying to find a needle in a haystack. The voxels of the brain are oftentimes at the cellular level, and to try and find activations and then associate them with kind of nebulous, poorly defined cognitive constructs can be challenging to say the least. I will attempt in this short lecture to kind of go over some of the key cognitive functions associated with influence and persuasion and put them in the context of kind of what we know about brain anatomy. So we'll begin with the nervous system, and this is mainly just to set the context. There's a central nervous system and peripheral nervous system. The central nervous system is the part of the brain, part of the nervous system that contains the brain and the spinal cord, and if it's peripheral, we're talking about the nerves that are located outside of the brain or the spinal cord. And why is this important? Well, all of our thoughts and behaviors begin in the brain, therefore you can't really understand influence and persuasion without some understanding of the brain. So we're going to focus the rest of this discussion on the central nervous system and in particular the brain. So there are two types of brain cells. There are neurons and glial cells. The glial cells are what's called the white matter, and the white matter, they don't really involve any actual thinking. They're there for structural support, for supporting the other neurons and kind of providing insulation on them, kind of keeping those networks in place so that they can function. The gray matter is made up of neurons, and these are, and we'll talk about those a little bit more in a minute. They're connected through very long spidery arms. They're very like kind of spider webby type cells, and they communicate through both electrical chemical signals as well as the release of neurotransmitters, which is another type of chemical. And these neurons are the building blocks of any kind of thought, emotion, memory, identity, who you kind of think you are as a person. And they're involved in any of the core processing for cognitive functions that we're going to be discussing. So we're going to talk about neurons. Neurons are the cells that are involved in actual thinking, thought. They are made up of three basic components. The first are dendrites, which are these input trees. If you look around the green structure there on your slide, and you see these little tentacles off the edges, those are the dendrites, and they receive signals, neurochemicals from other cells or other neurons, and those are kind of like the inputs into the cell. Soma is the cell body. Soma is Greek for body. So the green that you see there is the cell body. It has a nucleus like most cells. And then there's an axon, and the axon is this long structure that kind of goes down here. It's indicated in purple. And then they have these axon terminals, which are these like tentacles out here that kind of look like the dendrites, but these are axon terminals. These are the output of the cell. And so we're not going to go into a whole lot of the chemistry involved in neurons. If you're curious, please reference the textbook. But what we're interested in is detecting neural activity and how it relates to cognitive processes. So it's important to note that neurons are not silent. They're always active. There's always some level of activity going on there. So when we're looking at brain activity, we're not looking at, okay, there's no activity, 0, and we see some sort of electrical potential, oh, there's now activity. No. What we're doing is we're kind of comparing the levels of activation compared to some sort of baseline. So we believe that when there's no stimulus, those neurons are still firing off, they're still having some activity at a certain level. There's like a distribution. And then when they're exposed to stimuli, then there's a higher level of activation or higher level of activity. And so we can kind of compare between baseline and, under presentation of stimulus. There are electrochemical potentials that move across the neuron body, and those can be detected based on their electrical properties. That's how an EEG would work. But then there's also this release of neurotransmitters that kind of send signals between neurons. And so when that release occurs, it's usually caused by this electrical chemical potential across the neuron. But when those neurochemicals are released or transmitted, they need to be resupplied. And so they're resupplied with blood flow. And so there's certain methods that are detecting that resupply of blood flow from like functional magnetic resonance imaging or functional near-infrared spectroscopy. fMRI does magnetic properties of the blood and oxygen. FNIRS is using optical properties. So they're detecting the resupply, and there's usually about a 5 or 6 second delay between the actual firing of the neuron and when we would observe it in blood oxygen level dependent signal. So that's another consideration we have to have. So what happens in a neuron? Well, even if we're looking at like these electrical potentials, right? There's this resting potential as indicated with the little 1 there, and so there's some sort of potential. Then there is this threshold of excitation, which is exposure to some sort of stimulus, and then you'll see that potential peaks, and that's the peak action potential. And after it's peaked and it's kind of fired its electrical signal there. Then there's going to be this repolarization, and you'll see that it kind of dips below the resting potential and it overcorrects, and then it kind of levels out, and that's called hyperpolarization. So we see that there's this signal function that occurs, and when there's multiple firings, these can get compounded, and the more you compound them, the more potential error that can be occurred in estimating when the actual threshold of excitation occurs. We're now going to switch directions a little bit, and we're going to talk about anatomical planes. So when you look at a brain section or brain for imaging, right? There's kind of 3 ways in which you can cut the brain to take an image. So the first is axial, and you'll see that on the left with the green plane, and that's kind of like you're looking from the top of the head and you're looking down. So you can kind of imagine a whole bunch of different planes as you're going from the top of the head all the way to the bottom. And so you'll be looking at different areas, regions of the brain there, and so you might show like highlighted areas to show where there's higher brain activation in that axial view. The coronal view is kind of like you're looking at the face of a person, and you're slicing that brain from their face to the back of their head. And then the sagittal view is where you're looking at the profile of a person, and you're kind of slicing the brain from left to right or right to left. And so you can see that these are 3 different ways in which you can take a 3-dimensional object and look at it in 2 dimensions. And then what we would do is we would highlight or put some sort of color on top of those black and white images to indicate where there's actual activity. So you will see these referred to in the literature as either axial, coronal, or sagittal views. So those are key terminology. We also can refer to the directionality of the brain. And so it's important that we have, just like if you're looking at a map and you have north, east, west, southwest, you need to have directionality for the brain. So the first one we'll talk about is dorsal and ventral. So dorsal you see here at the top of the head, ventral you see at the bottom. And the way to think about this is, if you think about a shark, we've probably heard of their dorsal fin. The dorsal is on the back, right? So you'll also see that on the brain stem here and going down to the spinal cord, dorsal would be the back of a person, and the ventral would be the front. If you look at a dog, for example, the back or spine of the dog is the ventral side. The belly of the dog is, the back of the dog is the dorsal side. The belly of the dog is the ventral side. But because humans stand upright, this kind of gets a little bit messed up. So dorsal actually is referring to anything along the top here of the brain is the dorsal. Right? Again, just think of dorsal fin on a shark. The opposite of dorsal is ventral. And so this is going to be used to refer to kind of the bottom areas of the brain. We also have rostral. Rostral means nose, and caudal means tail. So we have the nose of the brain and the tail of the brain. Sometimes people don't like to use rostral and caudal, so they'll use anterior and posterior. Anterior is front, posterior is back. Right, so these are the key directions that we will have in the when we're referring to the directionality of the brain. So now we're going to talk about some key brain regions and what they do. So this is just a sagittal view of the brain, and so it's cut in the middle, if you will. And the first area we're going to talk about is the thalamus. So the thalamus, if you notice, there's this, the brain stem kind of comes up in here, and it has this really kind of small region right here. This is sometimes referred to as the reptilian brain. You'll see in the neuroscience literature, there's a lot of discussion about evolution, and so this is considered kind of the oldest part of the brain. Some people call it the reptilian brain. So the thalamus is where we relay all the senses except some of the olfactory senses, and it's almost in the center of the brain. And so this is kind of where our senses are being connected to our mind. So there's a lot of processing that goes there in the thalamus. The hypothalamus is this area just to the ventral and rostral edge of the thalamus, and it regulates some of the metabolic processes like your temperature, your hunger, thirst, also attachment processes for like infants, family. It also is involved with fatigue, sleep, circadian rhythm. So when you're tired, when light and ambient light is going to affect your desire for sleep or being awake, is all kind of controlled there in the hypothalamus. The pituitary gland is key part where the endocrine system and the nervous system kind of interact, and this is where a lot of stress, growth, energy management comes from. It's also highly involved in any kind of sexual organs, lactation, breastfeeding. A lot of that occurs from the pituitary gland. The amygdala is probably one of the most well-known brain areas. If you ask the layman, they probably have heard of the amygdala. And this is begins where to involve emotion, and where we are dealing especially with fear, anxiety, and aggression. The amygdala is also involved in decision making, and that's kind of where that fight or flight decision is the most common one people think of. But it's kind of where emotions begin to connect with higher order decision making in people. There are some key sex differences in the amygdala. So we actually have two amygdalas. There's a left and a right. If I showed you probably a different view of the brain, it would be a little easier to see, and there are some in your books. But what they find is when watching like horror films, as an example, they find that men will have greater activity in their right amygdala and women in the left. And so the right amygdala is often associated with negative emotion and with action, whereas the left amygdala is often associated with more positive emotions and also more thought. And so what's interesting is when you have a particularly emotionally salient stimuli, men tend to react with action more to negative stimuli. Women tend to have longer memories of positive stimuli. And so we find that like whenever you have positive stimulus, emotional stimulus, then people have lower levels of arousal but longer lasting memories. And if you have negative stimuli, you have higher arousal and shorter lasting response. And so it's kind of interesting that men and women behave differently in these situations. It's also one of the reasons why some speculate that women have stronger memories of emotionally salient memories. And that they tend to be more relational and thoughtful, whereas men tend to be more action-oriented. The amygdala is also where long-term memory is consolidated. So when you have all these short-term memories, they kind of need to be consolidated for storage into long-term memory, and so that is the amygdala is involved in that type of processing, in addition to the emotional-related memories. And it's also involved in some of the conditioning responses, especially fear conditioning. So again, the amygdala is a pretty important area, even though it's very small. The hippocampus is also involved in this short to long-term memory. It's also highly involved in spatial memory and conflict processing, which is one of these anomalies where everybody kind of wants to believe that, hey, a particular brain function is going to handle kind of related processes, but nobody can really find the connection between conflict processing and memory. The hippocampus, by the way, actually extends all along this area here. This kind of, it's like the floor of the thalamus, right? So whereas the amygdala is just this one spot right here. The basal ganglia is this region above the thalamus, and this is where we start to see sensor motor feedback. So this is where you're going to be dealing with like timing, action, precision, and so this is kind of where the thalamus, this relay of senses, begins to connect with higher level brain thinking. It's also involved in prediction error. So when we anticipate an outcome and something is different than what we anticipate, then this kind of triggers our system 2 thinking to say, hey, let's put some more thought into what's going on here. Something in our senses has kind of not behaved as we would expect, and then it kind of triggers our brain to top-down processing. And then it's also involved in motivation and learning as well. The corpus callosum is the largest white matter structure. Recall, those are glial cells, not neurons, but they allow a lot of the communication between hemispheres. And so there is that's this area that you see right here, above the basal ganglia and below the cortex. There are gender differences in men and women between the size of the corpus callosum. And so this is believed to be, some speculate that it is why women are believed to be better at multitasking and men are not as good at that task. The last area we're going to talk about on this chart is the cerebral cortex, and this is a large area of the brain, of course, and this is where all of our kind of cognitive function occurs: memory, attention, perception, cognition, awareness, thought, language, consciousness. Whereas everything kind of below that cortex is preconscious, so it's very difficult for us to be aware of or articulate what we're doing in our brain. Whereas when you get to more of the conscious thoughts, much easier to articulate. So we're going to look at a slightly different view here of the cerebral cortex. These are the areas of the brain that we're going to focus on a little bit more in depth. So a couple of vocabulary terms here. The first is sulky. Sulky are the crevices in the brain. So as you see these little lines here, these are folds. So one of the differences between like a rat brain and a human brain is a human brain has a lot more folds in it than the rat brain, and it allows us to put a lot more cortex into a smaller space than a rat. So the sulky are the crevices, and then the crowns of the folded tissues are referred to as gyri, or gyrus or sulcus if you're talking about a singular area, right? So this is the sulcus centralis, which is the crevice that is between two lobes of the brain, and you'll see other ones here that they have as well. All right, these are key sulci that break up the brain into essentially four lobes. All right, four kind of distinct lobes. So sulci is crevices, gyri is the crowns of the folded tissue, and there are four lobes in the brain. So each of these lobes has a kind of different general function. So in general, the auditory functions occur in the temporal lobe. So this is where we see hearing. The occipital lobe here to the back, or the caudal or posterior part of the brain, is where we have vision. The parietal lobe is where we integrate a lot of sensory information. It's also where we kind of process pain, its temperature. Even our limb perception is occurring in this area. And then the frontal lobe is where we have motor function. This is where we're actually directing movement of our limbs. We also have the executive function, which is things like our memory, attention, cognition, etc. And theory of the mind is used to refer to being able to understand that other people have thoughts, other people have beliefs, other people have different views, right? So usually this develops around age 4, but you might imagine a dollhouse. I don't know if anybody's ever had a dollhouse, but if you have a dollhouse, usually there's like the front of the house looks like the front of a house, but then the back of the dollhouse, it's like it's been cut so you can kind of see into the rooms and you can put the dolls and the furniture and whatever in there. So a theory of mind is necessary to be able to recognize that if you're looking at the front of the dollhouse, a person on the other side has a different view and might be able to see things there that you don't see and that you're not aware of. And so that kind of is theory of mind. It's very important for any of our social interactions or social processing. It's necessary for us to understand that other people might have different motivations and intentions that are dissimilar to our own. It's necessary to understand that people's opinions might be different, right? So that also occurs in the frontal lobe. The frontal cortex, we're going to divide this into a little bit further, can be divided into some distinct areas as well. One of the key ways in which we refer to different brain regions is with Broadman area. So that's BA. So Broadman was a guy that kind of did a lot of dissections of the brain and kind of identified these different regions. And so they kind of are used as one way in which people refer to certain areas of the brain. And there's a lot of them. I think there's 80 different Broadman areas. Some people have since come up with as many as 200 different regions of the brain that they refer to. Broadman kind of pioneered this work, so we often use Broadman areas, or they're often referred to in the literature as Broadman areas. And so I'm going to do a little bit of a mapping here and show you kind of different ways in which people refer to the brain. So the first one here is the red area you see is Broadman area 10. And this is in the lateral, meaning it's not in the middle, lateral frontopolar cortex. Right? So it's in the front of the and polar means the front pole, right? So it's at the very kind of front edge protruding part of the brain. This area is kind of preconscious decision. It's involved in approach or discuss. We'll talk about that a little bit later. Broadman area 9 is moving back along the brain, so it's moving to this yellow area, and it's kind of this region up here. And so Broadman area 9 is used in inferring the intention of others, right? It's involved in some of this theory of mind, assuming what are other people thinking, what are their intentions and motivations. It's also involved in spatial imagery or verbal auditory attention, and some of the prediction area we were talking about earlier. Moving down a little bit to the lower edge of this yellow region is Broadman area 46, which is more involved in attention and begins to become involved in some working memory. We then move into Broadman area 44, 45, and 47. And so that is 45 is kind of to the front corner here, 45, and then 47 below it. And this gets into processing of speech and music. Broadman area 8 is moving further along the dorsal edge of the brain up in here, and Broadman area 8 is involved in uncertainty, hope, and it kind of gets more into anticipation, and then it moves towards Broadman area 6, which is like the premotor cortex, which is kind of where your brain is integrating and processing these decisions about what type of actions it will take. The important point here is you see that there are a couple different ways in which we're referring to this. You'll see that there's anterior and posterior, rostral and caudal, dorsal and ventral, and these are directions in the brain. And then we have lateral, means towards the outside areas of the brain, so going from the center of the brain out. And then we'll see some of these other terms like lateral, prefrontal, dorsolateral, anterior, So these are all getting mixed up in various ways in which we're referring to regions of the brain. And it's important that we become familiar with some of these so that we can understand what the literature is telling us in terms of where these activities are occurring in the brain. We just keep getting more complex. So I'm going to break down the frontal cortex, and I'm going to show you some more from the sagittal view of certain regions in the brain and just give you a sense of what we believe their functions are in the brain. So the first is the orbital frontal cortex, orbitofrontal cortex, right? So that is OFC. And so we're looking at the medial orbital frontal cortex, which this is looking at the brain from the ventral side, from underneath. And so we see that this is kind of Broadman Area 14 and 11 is what the numbers are referring to here. And that is generally believed to be associated with goal relevance, internally generated goal relevance. So thinking about internal goals and how that might be relevant to whatever stimulus you're looking at. As we move to the lateral, and that's a lateral orbitofrontal cortex, right? We look at Broadman areas 11, 12, 13, right? 11, 12, 13. And these are also goal relevance, but externally generated goal relevance. So we're kind of thinking about external factors in the environment and how that affects us. The next area I like to focus on is this area in the brain. This is the sagunal anterior cingulate cortex, and so you see the ACC moves around this region. So it's above the corpus callosum, but it's kind of like there's kind of two groups of brain tissue, and so this is the first one between the corpus callosum and between this outer layer. And so the first area, the SGACC, is going to be responsible to physical response to emotion. So this is where we're taking our emotions and it's increasing heart rate. It's maybe increasing pupil dilation. It's affecting these physiological responses to an emotional reaction. As we move a little bit higher up here, and we're moving a little bit more towards the dorsal side here, is the PGACC, and this is where we kind of have some pain aversion or excitement, and so we have a little bit higher processing. And then we get to the AMCC, which is where we kind of are doing action valuation, and we're predicting outcome-based what might happen to us if we do this decision or that decision. So you see that we're kind of getting from emotional, and as we get more and more dorsal, we are having kind of more higher executive function or higher thought levels that we're having as we're processing stimulus. If we move our attention here to the green region here, where we have the dorsal medial prefrontal cortex, this is again where that mentalizing occurs, where we are praising the other's mental states. What are their motivations? What are they thinking? What are they doing? As we move down here into the rostral medial prefrontal cortex, this is where Broadman Area 10. This is where we are having more self-reflection, self-integration. This is where cognitive dissonance is believed to exist, where we begin to look at inconsistencies between our thoughts and our beliefs and our actions, and need to kind of make sense of that. As we move more lateral, so you'll see that not in the medial area here, but the lateral areas of the brain, this is where we start looking more at emotional control and self-regulation, self-control. So a person that is looking at a cookie and they have that excitement about how tasty that cookie would be, and the self-control says, you know what, that's going to make me fat. I don't want to eat that cookie. I'm not going to do that. Then that is activity that is occurring in the lateral prefrontal cortex as we're kind of engaging in that self-control. One particular area that is of interest to us is on the right side of the brain. So the right lateral prefrontal cortex is where we hypothesize that counter-arguing occurs. So when you are receiving information that is inconsistent with your worldview and would create some cognitive dissonance, it's the right lateral prefrontal cortex that tries to develop rational judgments as to why that information is untrustworthy or false. Okay, and you can see here that there are a lot of different areas of the brain, or labels for areas of the brain, and how they're referred to. And hopefully, this is giving you a better sense of some of these concepts as it relates to the frontal cortex, and as it relates to influence and persuasion literature. So we're going to develop those areas just to give you a model of social influence, and I'll give you this model of social influence as it relates to some of the anatomy we've just seen. So the kind of current view is that it's not like this orderly sequential process, right, where you do you sense the stimulus, then you have an emotional reaction, then you think about it for a while, and then you eventually make a decision in order. It's more that there's a lot of parallel processing that is all occurring at the same time, and all of these regions kind of cast a vote into what the brain is going to do. So let me put that in the context of an example. So let's say you are going and you need a new car, and you're going to decide between whether you want to buy this flashy sports car or this kind of cost-effective hybrid car. So we might think of the medial orbital frontal cortex as imagining the wind in the hair. So I'm assuming you've already sensed the car, you've kind of processed that, you're having some sort of emotional reaction to that car, right? And now it's kind of moving into the medial orbital frontal cortex, where you might imagine the wind in your hair, right? And how that how that's going to make you feel internally, right? This is this goal-oriented, hey, that's going to be awesome. Let's go for the sports car. The lateral orbital frontal cortex might be impressed a little bit more with external focus things, not the wind in my hair, but hey, that's cool color, that's a very nice design, that's aesthetically pleasing, right? So that's where you're more processing these kind of external goals, right, of goodness. The Sagunal ACC is the physical arousal that you're going to get from owning a sports car. As that moves up into the PCC area here, you then start thinking about the excitement you might get for owning a sports car and how cool that will be. And then it gets into the AMCC, and you start thinking about, I'm going to have to work longer to pay that higher price for the sports car. I don't know that the work is worth, and effort is worth the benefits of the sports car, and you start to have this trade-off. The dorsal medial prefrontal cortex is beginning to have this assessment of, hey, is the salesperson, what are they thinking? Their views and motivations and what they're telling me might be different than my own. They may be trying to sell me this because it's the more expensive option. They want to increase their commission. What are their motivations? Right? As those assessments move forward in the rostral medial prefrontal cortex, we might be making assessments like, hey, well, I feel young in a sports car. How is that going to how are others going to perceive me? How's that going to make me feel? Right? And so then we have all of these things going on, and then we still don't forget the lateral prefrontal cortex, which is where our brain is going to attempt to downplay our excitement and the immediate rewards and kind of weigh those against kind of future desired future outcomes. All of these areas of the brain are all kind of casting a vote, and then it kind of moves here into the premotor cortex as you begin to plan, hey, what actions are you actually going to take? And they're all kind of voting towards that. So that's one view of social influence. Now there's a lot going on here, and this causes a very important issue in the study of neuroscience, and that is of reverse inference. Reverse inference is you have a cognitive reaction that we understand. Like you have this emotional reaction, we can document it, we can see it, we can know that a person had a certain reaction, and then we identify certain areas of the brain were activated during that cognitive process. Reverse inference would be, okay, now here's another situation where we see the same or similar areas of the brain activated, and so we assume that the same cognitive process occurred. Well, you can look at the complexity of just this social influence model and see that, hey, if I were to notice that that there was region 8 here in the rostral medial prefrontal cortex is activated when every time somebody wants to buy the flashy sports car or the sales ad that they're looking at, then I may fall into the temptation of every time I see activation in that area, hey, they want to buy something, right? There's the buy button in the brain. Well, that's called reverse inference, and that's very dangerous because that area, as we understand it as being self-integration, is also involved when you're receiving a compliment, is also involved when you're weighing the view, conflicting political views. It's involved in a lot of other different things. So simply seeing that activated does not mean that it's a buy button, and you can assume that this person is going to buy whatever it is you've attempted to sell them in an ad. So we need to be very careful about that reverse inference. Some areas of the brain, it's even more problematic, like memory. Involves many regions of the brain, so kind of localizing is a person encoding a memory or not is very difficult, if not impossible, with our current levels of technology. Other areas or other processes, like to some degree attention, certain emotional processes, certain things like mentalizing, counter-arguing, some of these processes are more localized in the brain, and so therefore they're a little bit easier to detect. So we'll look at an example of some of those next. Here's some brain regions, and this comes from some work by Emily Falk and Matt Lieberman. Emily Falk is at University of Pennsylvania, and Matt Lieberman is at UCLA, University of California, Los Angeles. And so, I'll draw your attention to the upper right. So in looking at behavior change, the traditional method is self-report. You're going to ask people if they have a certain level of intention, and that can be, measured, quite well. You can get a third of that explained by self-report. You can also get a third of that by neural activity, and there's this overlap. So really the strength is that combining the two modalities gives you a much better understanding of likely behavior change that you might experience. And as we've discussed before, the self-report is particularly useful for conscious processes, things that are not taboo, things that are people are aware of, things that are highly conscious, right? So if I were to ask you, hey, are you male or female? Hey, what's your favorite color? What do you like? These things are things that people can report on fairly accurately. What you're feeling, what your emotional state is, these become a little bit more difficult. So if we draw your attention to the left, you'll see again that Emily Falk identifies the dorsal medial prefrontal cortex as an area where mentalizing may occur. And this is where you're thinking of the mental states of others and what are their beliefs, what are they thinking, how does that, what are they thinking of me? The medial prefrontal cortex, she would argue, is dealing with any kind of self-related processing regions. So this is where you're now beginning to internalize those ideas, internalize those stimuli. What does it mean for me? The blue areas, right, so the ventral striatum and the ventral medial prefrontal cortex are valuation regions, and these are kind of get in touch with the, or connected to the reward circuit. So, affirmation, how does this affect positive reward? How is this going to benefit me? That's what we're thinking here. And then we have this dorsal ACC that is, hypothesized to be affected with like conflict detection and response, dealing with those. You'll also see that there are some more lateral areas of the brain. So this is the temporal parietal junction. So this is where the temporal lobe and the parietal lobe meet. And so that is an area that is also thought to be involved with mentalizing areas or mentalizing regions. or it's highly active during those areas. And then the AI here, the anterior insula, is also believed to be dealing with conflict detection, conflict response, and that's part of the basal ganglia, in the brain. So this is a different model, and this is showing you different regions, and you see that they're somewhat similar to what was presented earlier, but maybe not as many regions. And so I think there's a couple points here. One is different people have kind of identified different regions of being important in a social influence process, but you also see that there's some similarity between these two. The other point is that what Emily and Matt have done is they've kind of focused this into a smaller set of important regions to help us understand social influence and how that might be affecting behavior. And it gives us a more focused or localized area to study for potential changes. Here is another social influence model, and this is another one that comes from Matt Lieberman at UCLA. And so if I can draw your attention to the right, there have been a number of studies that show that activation in the medial prefrontal cortex, right here, is associated with self-integration. The self-integration is kind of believed to be the process that goes on here. That activity here is strongly correlated with behavior change. And it may or may not be reported with self-reported behavior change. So as you saw in the previous example, while self-report is good for certain processes, other things that you're less conscious of, it's very difficult to know whether self-report is actually going to be tied to that change, right? I'll show you an example in a minute of one of their studies. There's localization of that is then found here in the medial prefrontal cortex as well as the PC-PCC area of the brain. Another area that we saw before was this orbitofrontal cortex ventral striatum. And as we said before, that is associated with self-affirmation. And in Lieberman and Fox studies, there's been high correlation between this self-affirmation process and increased activity in the medial prefrontal cortex. So whenever you're affirming somebody, people are more likely to receive the message. And that's well known from like persuasion research, traditional persuasion research, that people are much more receptive to messages that are accompanied with affirmation. The fact that they've detected a correlation of that in brain activity kind of helps support this model that these areas are connected. The areas in the dorsal medial prefrontal cortex and temporal parietal junction associated with mentalizing, thinking about the mental states of others, also have been associated with narrative immersion. So when people are telling a story, when you're seeing characters on a screen, it's that mentalizing, thinking of the mental state of the characters that's kind of engaging you in the story, right? It's kind of, the more you're kind of trying to infer what their goals and their motives are and what's going to happen in the story, the more engaged you are with the story. That's narrative immersion. To the extent that people are doing that, we find that they also have increased activity in the medial prefrontal cortex. We find that all three of these are negatively correlated, that's the dashed line, with this area in the right lateral prefrontal cortex, and that is associated with counter-arguing, right, in the right lateral prefrontal cortex. The boxes here and here are talking about the type of messages and the anticipated effect. So if I have rhetorical persuasion, which is ethos, pathos, logos, and I'm telling you information you already agree with, we find that that increases activity here in the medial prefrontal cortex. If, however, the information is counter to what you already believe, we find that that increases activation in the lateral prefrontal cortex, or counter-arguing, which is then negatively correlated with increased activity in this particular region of the brain. And then the narrative persuasion is, again, if you tell somebody a story and the story is matched, tailored to the target audience that you're attempting to influence, to the extent that it increases the narrative immersion activity in these regions of the brain, then it's also correlated with self-integration, which is then correlated with behavior change. So this is an attempt at a model to kind of tie several different regions of the brain together. So what we would want to do from an influence perspective is understand, are we targeting affirmation? If we are targeting affirmation, do we see activities in these regions of the brain? Are we targeting narrative immersion? Are we trying to tell a persuasive story? Do we see activation in these areas of the brain? Right? Are we attempting to create counter-arguing or reduce counter-arguing because we're telling a story or because we're affirming somebody in a view that we know is antithetical to what the target audience believes? Do we see reduced counter-arguing as a result of our intervention? Right. So these would be things that we would be interested in looking at based on this model. These are some results from a study by Emily Falk and Matt Lieberman. Emily Falk is at University of Pennsylvania, Matt Lieberman at UCLA, and they were looking at people's responses to 3 different commercial ads, public service announcements to call the 1-800-QUIT-NOW smoking hotline. So the graph that you see to the left are self-reported rankings. So this is kind of on a scale of 1 to 10. How effective do you think the ad is going to be? And you can see that everybody really liked ad B. A was okay, and C was a bit of a stinker. The middle graph shows the neural response in people as they were viewing the different ads. The graph on the right shows the actual call volume because these 3 ads were aired at different times, and so you could see how many people were calling at those different times. And so the call volume matches much more closely to the neural response in the medial prefrontal cortex than it does to self-reported rankings. Now I'm going to show you the winning ad number C, and then we'll discuss a little bit more about why this might be.
Steve, are you smoking?
Yeah.
Didn't we agree you'd go outside?
It's raining.
I don't see why you can't just quit.
Do you think I've tried? I don't know what else I can do.
You're a finger, Steve. You can dial 1-800-QUIT-NOW for free information and support. Please, Stevie.
Quitting is hard, but dialing 1-800-QUIT-NOW is easy. If you're ready to try, call for free information and one-on-one counseling.
So as you see in that ad, it's kind of silly looking, right? It's a bunch of fingers with Sharpie faces. And so you can kind of understand why people would not rate that particularly highly as an ad number C. But that doesn't mean that it's not effective. In fact, there's a lot of things about that appeal that it overcomes barriers that people might have by looking at a more well-polished ad. They might feel like they're being manipulated or influenced, and so when they see ad number C, they don't put up as much of a cognitive defense to the information, perhaps. A couple other things about this study. The people that were recruited for the study and shown the 3 ads were people that had said they want to quit smoking. So they might have been a little bit more receptive to the message than the general population. And of course, the ads were shown at 3 different time periods, so it's not clear that there weren't other environmental effects. Right? Perhaps it was a rainy season, and so that's why people were more likely to resonate with ad number C for that video, whereas the others were delivered at different times. So there's a lot more that goes into that. But this is one of the key papers that is showing the importance of using neural response above and beyond self-reported rankings to understand actual behavior. Here is some results. I know there's a lot on the slide here, but I'll walk you through these. These are results from a study that I did about a year ago in Amman, Jordan. And so I was interested in looking at the effectiveness of 4 different ads that were produced to reduce sectarianism among highly polarized Iraqi Sunnis and Shias. So the ad to the left was produced by the U.S. government, and it is an ad of a chess game, and there's these computer-generated graphic images, cartoons. It was very violent, and it kind of had Shia-backed militia forces and kind of Sunni forces. So the Shia kind of look like Hezbollah, and the Sunni forces look like Al-Qaeda, and they're kind of in violent conflict with one another. The second ad, I call it the nice video, is of two kids, and you see them playing, kind of growing up together, and then they go to pray, and it becomes apparent that one's a Sunni and one's a Shia, and then it fast forwards in time and shows them as friends. And this was produced by Bahrain to increase Sunni and Shia unity in their country. The third ad, we call Graduation, shows a grandmother being very proud of her granddaughter at graduation, and then there's an explosion, and then you see the grandmother crying over a photograph of her granddaughter, and it flashes to some imagery where it says, you know, ISIS is destroying families, don't let them destroy yours. The last ad is al-Bashir, and he is kind of like the Jon Stewart of Iraq. He's a well-known celebrity, and he produced a video. Even though he's a comedian, his video was very serious in nature, and it was just talking about the importance of reducing sectarianism, and he was kind of advocating that people not support a issue on the Iraqi election ballot to institutionalize militia forces. So when Iraq liberated the northern parts of Iraq from ISIS, that was largely done by militia forces that were sectarian in nature. They were either, for the most part, they were Shia, but there were a couple Sunnis, and so he was advocating that they not have these militia forces because of their religious affiliations. So these are the four videos. So I first looked to see, is there a change in the medial prefrontal cortex activity over baseline? So this is, the normal period as they're looking at a blank screen, and then they are exposed to the video. I average over the course of that video activation in the medial prefrontal cortex and see, is there a significant change from baseline? What we see is the only significant change was the second video, and we find that change was actually negative in direction. So quite different than what Falk and Lieberman found with their 1-800-QUIT-NOW commercials. Not sure exactly how to interpret that. In my personal opinion, the second video was the most boring of the four videos that I watched. We also looked at asymmetric frontal pole activity. So this is supposed to be associated with engagement or disgust. And so what we see is asymmetric frontal pole activity. This is a number that would be, this is looking at change, but the number would be low if there was a reduced level of engagement, or a disgust or a repulsion in what was viewed or seen. And so I'm showing you violin plots, which kind of gives you a little bit of a characteristic of the distribution, and you can see that there's really no statistically significant difference across these four different videos. If anything, you'll see that the graduation video was a little bit lower as a trend than the others. And that could be because of the, more violent surprise at the end, or it could be in the fact that, a lot of the students didn't identify very well with it because they were not college educated. We also looked at the potential change in right lateral prefrontal cortex activity, which would be associated with counter-arguing. And again, you don't see that there's any statistically significant difference across these areas, but you see that there tends to be less counter-arguing with the nice video. Some people had higher, counter-arguing in the graduation videos, but generally you see a very similar pattern. What's interesting is the chess video had a significant correlation between engagement and counter-arguing. They also had significant correlations between medial prefrontal cortex activity and that area in the right lateral prefrontal cortex that's associated with counter-arguing. In Model 3, if you recall, there was supposed to be a negative correlation between those activities. So the fact that we see this positive correlation is intriguing. We see this engagement between, or the correlation between engagement and counter-arguing statistically significant, and that interaction effect was correlated with a change in sectarianism over a 2-week span. So we assessed the level of sectarianism using a scale. It's an 8-item scale. It had an internal consistency rating of 0.78, which is pretty valid. And we find that there was a significant reduction only for people that identified with this violent chest ad and also had activation in that right lateral prefrontal cortex area as well. We also found some correlations between the self-reported levels of identification and counter-arguing. So we found that there were correlations for chess, NICE, and graduation, but none for the Bashir video. And also I would point out that for graduation, it was not so much right lateral prefrontal cortex activity and identification as self-reported. It was that right lateral prefrontal cortex activity and those who had graduated college. So people that had actually graduated college had increased right lateral prefrontal cortex activity for the graduation video. And all of those three were correlated with increased engagement. And so this is a very unusual finding, and we're still looking through the results. So what that shows you is that it's very possible to measure response to ads. However, the work as far as interpreting what those findings mean and our ability to make an assessment as to if we see this pattern of neural activity, it's a good ad, and this pattern of neural activity is a bad ad, it still eludes us, and there's still a lot more work that needs to be done in this area. So just to review some key concepts, some neural processes can be localized, others cannot, like memory is not a very good one for localization. You have to beware of reverse inference. So just because we see activation, we need to be very careful about what we assert as that is causing that activation. Some useful neural processes that we can use for persuasion research is that engagement discussed, and there is a measure that we see here, and your readings will have more detail on that. The attention index, this is a lot more well-defined in EEG work, but in FNIRS or fMRI, we kind of believe that that's activity in the left lateral prefrontal cortex or parietal lobe. The self-integration that you saw with the 1-800-QUIT-NOW ads in the medial prefrontal cortex is important. Counter-arguing in the right lateral prefrontal cortex. Mentalizing in the dorsal medial prefrontal cortex regions. Emotion is often deep brain and inaccessible to FNIRS, but it is accessible to fMRI and other modalities. Emotion is also easily detected with eye tracking and galvanic skin response, and there's other biometric tools that can get at emotion. And lastly, memory uses multiple brain circuits and still remains elusive in our ability to detect. So memory, recall is to date probably best supported with self-reported instruments. Thank you for taking the time to listen. This is Dr. Ian McCullough from Johns Hopkins University.